Now we'll look at Unit 10, and Unit 10 in calculus is all about series. Series are whenever we have lists of numbers that we add together. And this is an intense, big unit with all kinds of stuff in it, all kinds of things to learn. And it might feel like we're taking a bit of a break from regular calculus because we're not so much focusing on differentiation or integration, but really focusing on this concept of what things do as they go to infinity, which is limit-based, which is very much a calculus topic. In the first lesson, 10.1, AP topic 10.1, we have to just get into kind of what a series is, first of all. So I'm going to give you a quick overview of sequences and series that perhaps you've already had before. And these individual things necessarily won't be tested on an AP exam. They're just kind of foundational knowledge here. So let's go through these. First of all, a sequence, which we call A sub n, and you're going to see that all throughout this unit, it's any list of numbers where each term increases or decreases by some math operation. So, if we're going to say we're going to add 2 to every number, we're going to start with 3. Then we'd say 5, 7, 9, right? The list of odd numbers, we start at 1, I guess, would be a sequence where every term increases by plus 2. Now, if you want to know the fifth term of a sequence, then we say we want A sub 5. You can think of it as I want the answer A for the fifth term of the sequence. That'd be 9. Now, you may have learned about sequences in the past, and you've learned maybe in pre-calculus that sequences can be generated by adding or subtracting. We just added 2. That's called an arithmetic sequence, or by multiplying, dividing. That's a geometric sequence. So we could go times 2. Let's say we start at 3, then we go 6, 12, 24, like that. To divide, we just multiply by a fraction. Let's say we start at 3, we want to divide by 2, we'll multiply by 1/2. 3 halves, 3/4, 3/8, like that. Now, previously, you might have learned that a sequence's formula can be written in 2 different ways. A recursive sequence is a sequence where each term is built on the term immediately preceding it. So the next answer, say A4, would be 3 times the answer for A3, the answer before it. Or the next answer, A5, would be 3 times the answer for 4, A4. Now, the other way is called an explicit. Now, recursive is great, except sometimes we just don't know. Like if you want to find the 100th answer, that means you've got to know the 99th, because a recursive sequence is always built on the term immediately before where you're looking. So sometimes it's impractical, and we need something called an explicit formula, where each term is defined by which term it is. So if you want to find the 100th term, then you are going to have some formula where you plug 100 in for n, and then you do whatever else to the formula to get the answer. So 2 different ways that you might see sequences written. Now, whenever it comes to calculus and sequences, there's really just not a lot that you need to worry about. It says we might need to find the limit of a sequence. So as we go to infinity, like are our sequence numbers approaching something, where L is the number the sequence approaches as n increases. If the limit exists, then we say that the sequence converges to L. Now this is a really idea. Converging to a number means that we are that's the number we're approaching to, that we're getting to as we go to infinity. If the limit does not exist, then the sequence diverges. So what would be an example of a sequence that maybe would converge? So let's say we have a sequence defined by 1 over n plus 1, okay? And I'm going to say let's start with the 0th term, and we get 1 over 1. Then let's start with the first term. We get 1 over 2, or the next term. Then the next term, n equals 2, would be 2 plus 3, 1 over 3. N equals 3 would be 1 over 4. And so what happens is that as we go, we're getting closer and closer to 0, right? 1 over a million, 1 over a billion, 1 over a trillion. And so in this case, the limit as n approaches infinity of a sub n is actually 0. That doesn't mean they add up to 0. That's a series. We'll get to that in a second. That means that as we're going to infinity, our terms are getting closer and closer to 0. They're converging on the number 0. That might be the only real thing you have to do with sequences by themselves. Okay, what we are way more interested in calculus, and what's really the foundation for the entire rest of everything in AP Calculus BC, are series. And series are the sum, or maybe the part of the sum, that'd be called partial sums, of all the terms of a sequence. And so we use a summation symbol. You need to get used to this symbol. It's just a summation symbol. It looks like an integral symbol. They are closely related. We have a lower bound A and upper bound B, and we're gonna take the sum. We're gonna add up all the terms from the lower bound to the upper bound of the sequence. For example, if I go back up to the top and I wanted to find the sum from the first term to the third term of this first odd number sequence, then that would be 1 plus 3 plus 5, which would be 9. Now, that's called a partial sum because we only looked at part of them. We could go to infinity, and in this case, it's impossible to know. It diverges. So we actually cannot come up with an answer for that. So back to number 5 here. Or actually, let's just jump to number 6. So in calculus, we are very interested, almost exclusively interested, not quite but almost, in infinite series. So what happens as we keep adding these numbers up to infinity? Now your first thought might be like, well, that's always going to diverge. We're never going to get an answer. But that's just not true. Excuse me. We have many series that as we add them up, they actually approach a number. The series would usually have to be decreasing as we go up. So it's getting smaller and smaller and getting closer and closer to a number. Now, in calculus, let's read this again. In calculus, we're very interested in infinite series that start at a number, usually n equals 0, n equals 1, and keep adding its terms to infinity. So just keep adding and adding and adding and adding. And we'll look at an example in a second. Let's read number 7. This is perhaps the most important part of this whole first topic. If we can find that a sequence of partial sums, so maybe only the first 5 or 6 added together converges to a limit, to a number, then we can say the entire series also converges to that limit, and the entire series evaluated to infinity. That means that if you can find a pattern in the sums of the first few terms, like the sum of the first, sum of the second, sum of the third, then that pattern will apply to the series as it goes to infinity. Let me show you exactly what I mean here. So let's say we have a sequence defined by 1 over 2 to the nth power. And let's say I wanted to find the sum of the first 3. So that looks like an integral sign. Now let's fix that. And let's say just the letter S to the first 3. Okay, so that will be, and I guess we'll just define that n starts at 1. So 1 over 2 to the first power plus 1 over 2 squared plus 1 over 2 third. So that's 1/2 plus 1/4 plus 1/9. And let's just see on my calculator, 0.5 plus 0.25 plus 1/9 is let's do a wavy sign, about 0.861. Okay, so that's fine, but what's that mean? Like, what if we added a fourth term? So we have that 0.861 plus 1 over 2 to the fourth. Well, I still have that number in my calculator. I'm going to add to it plus 1 divided by 2 to the fourth power. And oh shoot, you know what? This should say 1/8. Yeah, timeout. If you caught my mistake, then thank you. Let's back all up. So 1/2. So 1/2 plus 1/4 plus 1/8. 2 to the third power is 1/8 is 0.875. There we go. So 0.875 plus 1. divided by 2 to the 4th power. Now that becomes 0.9375, and actually I don't need the wavy lines because for the time being I don't need to round. Those are exact. The sum of the fifth would be all of that plus 1 more power, so 1 divided by 2 to the 5th power, 0.96875. And so it appears that we are approaching 1. And so if we keep doing this, perhaps that's what we're doing. Well, so what we want to know is, what's happening if we find the sum all the way to n, if n is approaching infinity. So what we can do is, if we can find that we're approaching 1 there, then it works. So let's find the limit as n approaches infinity. Now, what we need to do is we need to figure out what's actually happening here as we are increasing another term. And so we could do a little bit of math, and we could figure out that every term is 2 to the n power minus 1 over 2 to the n. So if we evaluated the limit as n goes to infinity of 2 to the n minus 1 power over 2 to the n, we'd find that that gets to be 1, which is what we kind of started to see. It looked like we were getting closer and closer to 1, and in fact we are. So that's kind of a big idea. Now you might be wondering, okay, how did you come up with this equation here? Well, that's not quite as important. That would be your pre-calculus skills of coming up with explicit formulas. So if you need to review some of that, you might look back at some pre-calculus notes on recursive formulas. But at the end of the day, the limit of that infinite formula does go to 1, and we can see our partial sums go to 1 as well. And so again, this is the most important idea, that if you can show that your sequence of partial sums is approaching a number, which they were going to 1, then the entire thing will as well. Okay, this is just a quick start to sequences and series, and really series are the whole idea. After this lesson, there is a lot to learn, and most things individually are not crazy hard. It's just a lot to keep organized.